So today we will be covering solutions of linear homogeneous equations and the Wronskian. In our last lecture we covered solutions for equal real roots, distinct real roots, and complex roots for second order homogeneous differential equations. Today we will be focusing on the fundamental sets of solutions and the Wronskian and many solutions of linear homogeneous equations. A fundamental set of solutions is the fundamental functions that form a function, a solution function. Okay? Well, in this example, we have our solution function y, and our main functions involve e to the r1t and t e to the r2t. And since e to the r1t and t e to the r1t are linearly independent, we will be covering this very shortly. These form fundamental sets of solutions because you're going to drop the constants, and when you don't have the constants and these are the affecting terms of y, they basically form the fundamental sets of solutions. So basically when you have a function involving your variables such as t, your variables will be the pieces of your fundamental sets of solutions. However, you might have cases like 5x and comma, let's say 20x. Okay, well, these do not set a fundamental set of solutions because our variables are x as the same function. We have literally the same function. So it doesn't matter the constant numbers are different. These do not form a fundamental set of solutions because they are technically linearly dependent. Now let's focus on these ones. For distinct real roots, our main functions that play a role in this solution is e to the r1t and e to the r2t. Complex roots will be e to the at multiplied with cosine of bt, because look, these are the functions that include t, our input variable, and we just dropped the c1 because it's unnecessary to put it in a fundamental set of solutions. Likewise, we have e to the at sine bt, and that is also part of the fundamental set of solutions. Now I'd like to cover a very important concept in differential equations called the Wronskian. Okay? Well, the Wronskian is a determinant of this matrix. Okay? We will put our first solution y1 and our second solution y2 in the same row. y1 prime and y2 prime will go on the second row, and we will take the determinant. The determinant means multiplying for this 2 by 2 linear matrix. Of course, there are different ways to find a determinant of a 3 by 3 matrix, but in this course we'll be only focusing on 2 by 2 matrices. We'll be multiplying y1 and multiplying y2 prime, basically cross multiply, and subtract the multiplication of y2 and y1 prime. So basically multiply these diagonal terms and subtract the other two diagonal terms, okay? And you get this equation, y1 multiplied with y2 prime minus y1 prime multiplied with y2. And we have two cases. If equal to 0, if equal to 0 must go here. If they're equal to 0, and if they're not equal to 0, okay? Well, if we get a non-zero number from the Wronskian, that means that our solutions are independent. They form fundamental set of solutions. Okay, they can form a fundamental, and they do form a fundamental set of solutions. This is very important if it's not equal to 0. Okay, if it is equal to 0, then they are linearly dependent on each other, and they do not form a fundamental set of solutions. A very easy way to understand these concepts is if you have different functions. Okay, let's say you have e to the t, and you have t to the t. Okay, this t is obviously a different the same variable, but you know, you multiply with t, which is creating a whole different function. Then these are gonna form a fundamental set of solutions because they are linearly independent. But let's say if you have 5e to the t and e to the t, well, these will not form a fundamental set of solutions because they are linearly dependent. If you had e to the minus t and e to the t, well, they still do form a fundamental set of solutions because this is a completely different function than this one is. So when you look at it, you can kind of tell when a function is linearly independent from one another. However, the Wronskian is a very useful, handy method to verify this dependent situation. And then if you can form a fundamental set of solutions, it will be very helpful in the future for us using undetermined coefficients method, and we will need this information a lot in the future. So please take a note on this concept, and I hope you don't miss anything we are covering right now. Now let's start with a very nice example. Find a Wronskian of the given pair. Okay, so in order to find the Wronskian, we were creating this matrix with the first solution, e to the minus 2t, and the second solution, e to the e to the minus 2t. Okay, and now we're going to take the first derivative of this function inside this matrix, and the first derivative of e to the minus 2t is negative 2e to the minus 2t. And the derivative of this one will be a product rule, and you will have e to the minus 2t minus 2t e to the minus 2t. Alright. And now what we're going to do is we're going to cross multiply. And first of all, I'm going to multiply these ones and subtract the multiplication of this one. So when you multiply this two, you will get e to the minus 4t minus 2t e to the minus 4t, and minus, and we're going to now subtract this multiplication, minus 2t e to the minus 4t. Well, this minus and minus will give you a positive, so you will have e to the minus 4t equals your Wronskian. Okay? Well, you do get a non-zero solution. Okay? And remember, guys, you don't need to get a constant. Even if you get a function of t or a function of x, it doesn't matter. It still means that this is not equal to 0, because a function obviously could be equal to 0, but once you get that function, it ultimately is dependent on the domain of the function. So you will consider it to be linearly independent in this case. So Wronskian not equal to 0, so fundamental set of solutions will be y fundamental would be e to the minus 2t, comma t e to the minus 2t, because the Wronskian is not equal to 0. And you can also add they are linearly independent. Okay? Well, since they can form a fundamental set of solutions, that is quite implied, but you're free to write that in your exam. Now let's solve this wonderful exam problem. Please try to pause this video and solve this question on your own, because this is very good question. Okay, now the Wronskian of f and g is 3e to the 4t, and if f of t equals e to the e2t, find g of t. So first of all, we know that the Wronskian of f and g is this 3e to the 4t, and we know what f is. So why don't we start with building the Wronskian? So e to the 2t, this is going to be f, and this will be 2e to the 2t. Okay? And over here we have g, because we're writing g because we don't know what g is, and we have g prime of t. Okay, now let's find a determinant. The determinant is these multiplications and subtracting that from the first one. So you're going to multiply e to the 2t multiplied with g prime of t minus, okay, minus, please memorize these guys, 2e to the 2t g of t equal to, and we know that the Wronskian is equal to 3e to the 4t. Okay. Now that we have this equation, let's divide all sides with e to the 2t. So dividing this side with e to the 2t would give us g prime of t minus 2gt, and the right hand side will be 3e to the 2t. Now many of you ask, well, we have two variables and we only have one equation, right? How are we going to solve this? Well, the answer is we're not going to solve this by using algebra, but we're going to solve this using differential equations. This is the beauty of differential equations that comes in. So now you know that this is a first order differential equation, okay? You have your g prime of t and minus 2g of t, and you know how to solve these equations. You either use separable, which I don't want to use it because this is not the best case to use separable. Obviously, you can still solve it, but the best way to solve this differential equation is integrating factor, okay? Integrating factor from a few lectures behind. So integrating factor was basically using I of t, multiplying both sides with I of t, but first I of t is going to be e to the integral of p of t dt, and this will be, the constant will be p of t, which is now negative 2 in this case, and then we're going to multiply both sides with I of t in this equation, and then that will generate us a very nice form where we can pull out the g, and now we can integrate the right hand side and solve it. So let's do it. Now the p of t is negative 2 in this case, so we will have e to the integral negative 2 dt, and this will give us e to the 2t, negative 2t. Okay, now that our integrating factor is this, we can multiply both sides, and e to the negative 2t. I'm not going to multiply these one by one because I know for a fact that this has to be the case because we didn't make a mistake on the way, and this is what you should get when you're doing integrating factors. You're going to have e to the minus 2t gt and the product derivative. If you want to check that, we can product derivative this and get the same result, but ultimately what you will have is this product derivative equal to, and e to the minus 2t multiplied with the right hand side will just give you 3. Okay, now let's integrate both sides. Integrating left hand side will just get rid of the derivative due to fundamental theorem of calculus. So we will have this equal to integral of 3 dt. Okay, and this will be e to the minus 2t gt equal to 3t plus c. And then in order to find g, you're gonna divide it with that, 2t divided by e to the minus 2t plus c divided by e to the minus 2t. And this will be your solution of your differential equation. Now let's solve this very nice problem. Verify that y1 and y2 are solutions of the differential equation. Determine if they form a fundamental set of solutions. Well, as we covered previously, we can just tell it directly by looking at it because we're multiplying two functions here, but we have only e to the t, but this causes a big difference. However, we should still do Wronskian since the question is asking us to do it, but I'm just giving you this trick because a lot of the times you need to know beforehand what you're doing and what kind of functions you're dealing with. So please try to be familiar with how these functions look like, so they will be useful in the future. So now we have this differential equation. Okay, this is a second order differential equation, homogeneous differential equation, and our goal is to verify that these are solutions of the differential equation. So there are two ways you can verify this. You can solve this differential equation, which you should know already because we covered this. This will be r squared minus 2r plus 1, and you will ultimately have r minus 1 squared, and this is e to the t, c1 e to the t plus c2 t e to the t equals to y. This will be your solution. Okay, however, another way is to plug these y1 and y2 functions in and now you can verify that if they satisfy the equation. Since these are just constants, I can just tell that e to the t matches y1 and t to the t matches y2. But just for the sake of this problem, I will go ahead and plug these these functions in to see if they work, just to show you. So let's now start with forming the first derivative of y prime. It's going to be e to the t, and the second derivative is also e to the t. Okay, that's not a good t. Okay, now e to the t minus 2e to the t plus e to the t equals to 0. Is it true, guys? Yeah, this is true. These are just going to be 0. So y1 is definitely a solution for this function. And now let's check y2. Now let's form the first two derivatives of y2. So y2 prime will be e to the t plus t e to the t. Okay, y2 double prime will be e to the t plus e to the t plus t e to the t. Okay, the derivative of e to the t is e to the t. This derivative is going to be e to the t plus t to the t from product rule. So we have these derivatives. Now let's go ahead and plug these in. So y double prime, e to the t plus, actually 2e to the t plus t to the t minus 2 times y prime, e to the t plus t to the t, plus y, which is t e to the t in this case. So now we're going to have 2e to the t plus t e to the t minus 2e to the t minus 2t to the t plus t to the t. Well, this one and this one adds up to be 2t to the t, and we have a minus 2t to the t, so these can just cancel. And 2e to the t and 2e to the t cancel, so equals to 0, which is true. So y2 also satisfies this differential equation, which we also proved in the beginning using the solution method for second order homogeneous differential equations. Now we're gonna go ahead and find the Wronskian of this solution sets, right? Yeah, determine if they form a fundamental set of solutions. What this means is we need to know if these solutions are linearly independent or not. And the best way you can prove this mathematically is using the Wronskian, okay? So now let's use the Wronskian. The first solution was e to the t, and the second solution was t to the t. And the first derivative is e to the t, and the first derivative for this one will be e to the t plus t to the t. Let's cross multiply, and we will get e to the 2t plus t to the 2t minus t to the 2t. So this will be equal to e to the 2t, which is equal to Wronskian, which is not equal to 0. Okay, this is very important. This is not equal to 0. If it's not equal to 0, they do form a fundamental set of solutions, and they are linearly independent. Okay, these are very important notes, guys, very important. Please know how the Wronskian works and what happens when the Wronskian is 1 equals 0 or not equal to 0. If the Wronskian is equal to 0, they are linearly dependent and they do not form a fundamental set of solutions. However, if the Wronskian is not equal to 0, they are linearly independent and they do form a fundamental set of solutions.